All right, so if we remember, we started out talking about the heme part of hemoglobin, right? So it has like a nitrogen, 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 nitrogen here. All these have lone pairs that are on this iron 2+, and then they're all connected here, here, and here, right? Basically, and that whenever you turn it a little bit, you get the iron out of the plane when it's deoxygenated, and like this, and then nitrogen here, right? And then there's this the proximal histidine that is, excuse me, the proximal histidine that is holding on to the iron, keeping it from being, the proximal histidine is to coordinate with the heme, right? So it sticks the heme to the actual protein, because this is connected out here, right? Yeah, out here to the rest of the protein. So that's the proximal histidine, and that's its job, is to connect the iron to the rest of the protein. This is iron 2+, right? And then there's this other histidine out here somewhere, right? That is, I don't want to screw this up, so I'm going to try to draw this right. N 2H2 looks really bad, but there's this other histidine here, the distal histidine, right? That one's job is to, whenever oxygen comes, it'll bind here to this other side of the iron, right? There's oxygen, there's 2 molecules here. It will hydrogen bond to a lone pair on this oxygen here. That makes the oxygen less likely to reduce this iron 2+ ion, because iron 2+ is good. Iron 3+, bad. Bad. It does not bond to oxygen. Iron 2 does create a coordination with oxygen. And then we talked about myoglobin, basically. And so myoglobin, right? We have the KD of myoglobin, which is like the concentration of myoglobin times the quote-unquote concentration of oxygen. Usually we talk about impartial pressure, and over the concentration of the coordinated complex. And then we talked about the fraction bonded, right? Yeah, the fraction bonded. The fraction that has O2 bonded to it. And so we said that that is actually equal to the concentration of O2 over concentration of O2 plus the dissociation constant. And another way to write that is also pressure of O2 over partial pressure of O2 plus this dissociation constant. I think. And there's also the relationship that the dissociation constant is also the concentration of oxygen where 1/2 is bound. And you can kind of see why that's the case, because like if these two are the same value, this becomes 2 of whatever, this is 1 of whatever. 1/2 gives you 1/2. So yeah, that is pretty much all the fun. Now for the actual studying part. All right, so let's face it, we're gonna have a thing where we have to talk about we're gonna have a problem where we're gonna have to answer the percentage bound of oxygen and myoglobin. So what we're gonna wanna do, all right? So remember our formula, right? Our YO2 is equal to PO2 over PO2, or pressure of O2. This isn't negative log, this is pressure, plus KD, right? So there is 1, 2, 3 unknowns. So there are 3 possible problems he could give us, right? He could ask us to find the fraction bonded at O2, at a pressure of O2, and with this KD. Excuse me. He could have us find the pressure of O2 with knowing the fraction bound and the KD, which is also not too hard. Oh, sorry, chat is here. Can you show the whole page? Oh God, am I not? There we go. Sorry. Okay, so we can do that. We can do that. Let me actually pin my video. There we go. So I can actually see whenever I am. So, and then he can also ask us to find the KD given YO2 and pressure of O2. So we should probably have formulas for each one of these so that we don't have to waste time on it. So the formula for KD, let's start off with that one. So we have this formula starting out right here. PO2 plus KD. That should be like so we multiply both sides by the bottom here, so we get YO2 PO2 plus KD, that KD times YO2 is equal to PO2, right? Subtract that, we get KD is KD, or YO2 KD is PO2 over Y. That doesn't, no, it's not divide, sorry. And then KD is equal to PO2 minus YO2 PO2 over YO2. All right, now let me simplify this real quick because this is probably a mess. So we have our KD is equal to PO2 minus YO2 PO2 over YO2, right? So I guess we can pull out PO2 from this. So KD is equal to PO2 times 1 minus Y2 over Y O2 and this is just KD is equal to PO2 times O2 minus 1. Okay, so that is our full formula for this one. Can y'all see that all right?
Yeah.
All right. Okay, and then what was the other? PO2. So I'm just going to start writing it as O2 because that annoys me. So we start from our original thing that Y is equal to O2 over O2 plus KD. Then we get Y O2 plus Y KD is equal to O2. Y KD is equal to O2 minus Y times O2. Then Y KD is equal to O2 times 1 minus Y, which then means that O2 is equal to Y KD over 1 minus Y. Boom. And then Y is equal to O2 over O2 plus KD. So these three formulas are the only ones that we should need. All right, because remember the whole thing about this, these tests are how fast can you do them, right? So if we can shave off some seconds early, that's nice, right? All right, let's do some calculations problems. All right, so some calculation problems. So I'm gonna give you a Y that is, let's say 83. I'm gonna give you a KD that is 2. Yeah, no. Yeah, 2 torrs. All right, tell me what the oxygen concentration is. You have, we'll give you like a minute. Go. And I'm also going to have the formulas here just because we're practicing. So right there, boom. All right, time's up. Were y'all able to get an answer in that time?
Yes.
I got 9.8.
9.8. Oh no, wait, never mind. Sorry, I hit that twice. Yeah, I got 9.8. All right, good. Okay. So I've got a fraction of oxygen bound at like 71. And my KD is 4 torrs. What's my O2? You have 30, I'll give you 40 seconds. Go. All right, time's up. Did y'all get an answer in that time?
4.9.
9.8?
9.8.
Did I do it wrong? Let me check. So 0.71 times 4, right?
Oh my
Divided
god.
by one minus the fraction. All right, let's try a bit more of a complicated problem. So I've got 21. So I put in a certain amount of myoglobin, right? I've got 21% of that left of that myoglobin not bound. All right, my KD is still 4. What's the oxygen concentration? You have a minute. Go. All right, time's up. What did y'all get? 15? All right. You get that, Charlie?
No, I had to, like, I was messing with my dog. I didn't even look back up.
Okay, so remember how we did this, right? So if 21% of it is still bound, right? That means 79%. So 79% of it is, or sorry, 21% of it is not bound. 79% of it is bound. So that's y is equal to 0.79. All right, here's going to be a complicated one. I just thought of this type of problem. All right, so bit of a complicated problem. All right, so I don't actually know if this is the case, but I'm going to make up something. All right, so there is a wavelength at which the myoglobin that's not bound absorbs, but the myoglobin that is bound doesn't. So not bound, absorb, bound, doesn't. All right. So I put my myoglobin into solution in an anoxic environment, right? So no oxygen was present whenever I put it in there, okay? Then I took an absorbance, right? So the initial absorbance was, let's say 0.817, all right? Then I introduced an unknown amount of oxygen into my myoglobin, all right? Took the absorbance at that time, and I had an absorbance final of like 0.261. All right, you tell me. Oh, so and KD is still 4 torr. All right, you tell me what is the partial pressure of the oxygen. All right, you have 3 minutes. Go. Oh, sorry. One more thing. Pause. The molar absorptivity of, so whenever I took the absorbance, the molar absorptivity of myoglobin is like 8.21 inverse molar, inverse centimeters, and the path length was 2 centimeters whenever I took the absorbance for both of them. All right, go. You have 3 minutes. All right, time is up, and it is okay if you didn't find an answer to that problem. I even got the wrong answer to the problem. I'm an idiot. Okay, so first of all, how far did y'all get? Like anywhere at all, or were you just like stumped the entire time?
I mean, I basically just calculated the concentration.
All right, so you picked up on that, right? You picked up on the use Beer-Lambert's law, right, to calculate the concentration initial of the unbound myoglobin and calculate the concentration final of the inbound myoglobin, right? I assume you also figured out that the initial, so myoglobin concentration initial minus the myoglobin concentration final should give you the amount that is bound. Does that follow? Sorry?
Yes.
Okay. So, and then we also know that the fraction, right? We have an equation for it, right? But another way to write the equation is, so the fraction bound is the amount of this over the amount of this plus the amount of this, right? Which is also just the initial concentration of that. So y is equal to the bound over the initial. Okay, and from there you can go and do the whole pressure of O2 is the fraction times the KD over 1 minus the fraction. So from there you can just plug and chug, right? Let me actually go back and, oh, I lost it. Hang on. Let me go and actually do it again real quick. So 0.817 divided by 2.81 divided by 2. I was almost going to think of like not giving you guys this and like just taking the ratio of these two, right? But that doesn't really work. Well, actually, would that work? Come to think of it. Would it work? Huh. So I guess the ratio of this absorbance over this absorbance, right? So the absorption final over the absorption initial would give you the ratio of it that's not absorbing. Does that make sense? So like ABS final over absorbance initial should be equal to 1 minus y. Yeah, I don't even need to give you I don't even need to give you whatever I used. Just as long as I say I used the same path, the same setup for both of them. Huh, that's interesting. All right, so that's a problem. I bet you a nickel he's going to give us something like that. Okay. Let's see, is there anything else we can really do with the stuff we learned today? I can't really think of anything else. So I think I'm just going to call it an early night. Go and hang out with my girlfriend.
Well, y'all have a good night.